Today we're going to be using laws of logs to solve equations. On these ones, we're going to get them set up so that way a log is equal to a log. As long as we have log base b of m is equal to log base b of n, that means they have a log equal to a log and they share the exact same base, then we can actually ignore the logs and set our arguments equal to each other. Let's take a look at example 1. I have log base 7 of 3x plus 5 is equal to log base 7 of, I have a log equal to a log and they both have a base of 7. So I can ignore my 7s completely and I can go ahead and set my arguments equal to each other. So I'm going to write 3x plus 5 is equal to 8x minus 12. Well, now I'm just going to solve for x. I want my x's on one side and my numbers on the other side. I'm going to subtract 8x from both sides. I end up with a negative 5x plus 5 is equal to a negative 12. I'm going to subtract 5 from both sides. And I get negative 5x is equal to a negative 17. And then I'm going to say, let's get rid of the negative 5 by dividing by a negative 5. And I end up with x is equal to 17 fifths. And this is my answer. Now, if you remember, whenever we have a polynomial, we can't have a negative number inside the argument because we're not allowed to take the log of a negative number. So what I'm going to do is I'm going to plug that 17 fifths back in for my x's and see what that gives me. Because as long as it's a positive argument, we know that it's going to work. So remember, the argument, the whole thing, must be positive. So now I'm going to plug it in. I have log base 7 of 3 times 17 fifths plus 5, close my parentheses, is equal to log base 7 of 8 times 17 fifths minus 12. You would get log base 7 of 15.2 is equal to, and if you were to multiply 8 times 17 fifths minus 12, you would get log base 7 of 15.2. And we know that these are equivalent values, so it works out. Let's take a look at example 2. On example 2, whenever I have this, it says 3 log base 2 of x is equal to log base 2 of 27. Well, this is a log equal to a log, but there's a 3 in front that's messing us up. So we're going to make sure that we condense as far as we can. So make sure to condense. I know this 3 is really an exponent, so I'm going to put this 3 back on the x as an exponent. I get log base 2 of x cubed is equal to log base 2 of 27. Well, now I have a log equal to a log. They have the exact same bases, so I can ignore my logs and my bases and set the arguments equal to each other. So I have x cubed is equal to 27. Well, if I wanted to get rid of the cubed, I could take the cubed root because I know those are inverse operations. If I take the cubed root of both sides, I end up with x is equal to 3 because 3 times 3 times 3 gives me 27. And 3 is positive, so I know if I were to plug it back in for my x, I would be able to have a true statement. On example 3, I have log base 2 of x is equal to 2 log base 2 of 3 plus log base 2 of 5. Now on this one, I have to condense the right side. In order to condense it, I'm going to move this 2 back on the 3 as an exponent. So I have log base 2 of x is equal to log base 2 of 3 squared plus log base 2 of 5. I know 3 squared gives me 9, so I end up with log base 2 of x is equal to log base 2 of 9 plus log base 2 of 5. Now that we have addition, I can condense that further into multiplication. So I have log base 2 of x is equal to log base 2. And remember, when you condense, you write the log base 2 one time, and then you multiply 9 times 5. Well, I know 9 times 5 is going to give me 45. So I end up with log base 2 of x is equal to log base 2 of 45. And now I have a log equal to a log. They have the exact same bases, so I can ignore the logs and their bases and set the arguments equal to each other. So I get x is equal to 45. This is my answer. And I know if I were to plug in a 45 in for that x right there, I could work that out because it's not a negative number. On example 4, I have log base 8 of 48 minus log base 8 of x is equal to log base 8 of 4. So if I wanted to work out this problem, I know that I'm going to condense the left side. Whenever there's subtraction, I know I'm going to have division. So I write the log base 8 one time. I'm going to go ahead and put my fraction bar. Since the 48 has a positive log in front of it, it goes to my numerator. Since the x has a negative log base 8 in front of it, it's going to go to the denominator, is equal to log base 8 of 4. I have a log equal to a log. They have the exact same bases. I'm going to ignore the logs with their base and set the arguments equal to each other. So I end up with 48 divided by x is equal to 4. Well, I want this 4 to be a fraction because it just makes my problem easier. I'm actually going to rewrite this so it is 4 divided by 1. And now I can just cross multiply. 4 times x gives me 4x equals 1 times 48 gives me a 48. I'm going to divide by 4, those go away. I get x is equal to 12. If I were to plug 12 back into my logarithmic problem, I would be able to work this out and get a true statement. On example 5, I have log base 7 of x plus log base 7 of x minus log base 7 of 3 is equal to log base 7 of 12. I know I have to condense the left side. Now, I have addition and subtraction, so I know there's going to be a fraction. I'm going to go ahead and write my log base 7 one time. I'm going to go ahead and write my fraction bar. On this first log base 7 of x, I have a positive log base 7 in front of that x, so I'm going to put an x in the numerator. Then I have another positive log base 7 of x, so that x also has to go in the numerator. And then my 3 has a negative log base 7 in front of it, so that 3 has to go in the denominator, is equal to log base 7 of 12. Well, x times x gives me x squared, so I can rewrite this and say I have log base 7 of x squared divided by 3 is equal to log base 7 of 12. Now, whenever I have this, I can say, okay, it's a log equal to a log. They share the exact same bases. We're going to ignore the logs and their bases and set the arguments equal to each other. I end up with x squared divided by 3 is equal to 12. And I'm going to go ahead and write it as a fraction, so over 1. Now, I'm going to go ahead and say, okay, 1 times x squared gives me x squared equals, and then 3 times 12 is going to give me a 36. Now I'm going to go ahead and take the square root of both sides. Well, the square root of x squared is going to give me an x. The square root of a 36 can be either a positive or a negative 6. Now, this is where it becomes a little bit tricky because of the negative answer. If I were to plug in the negative sign with that x, I would have log base 7 of negative 6. And we know that we cannot take the log of a negative number, so we cannot have the negative part of the answer. So we have to make sure that we only use the positive 6. I can say x is equal to 6, and this is my answer. Let's take a look at example 6. On example 6, I have log base 2 of 2x minus 1 minus log base 2 of x plus 5 is equal to 1/2 log base 2 of 36 minus 2 log base 2 of 2. Now this looks very complicated. Well, you have to condense both sides. I'm going to condense the left side, and I'm going to condense the right side. Whenever I condense the left side, I can see I have log base 2 minus a log base 2. The subtraction tells me I have to have division, so I write log base 2. I need my fraction bar. The 2x minus 1 has a positive log base 2 in front of it, so that goes to the numerator. And the x plus 5 has a negative log base 2 in front of it, so it has to go to my denominator, is equal to, and then I can see that I have exponents on the right side. So the 1/2 is going to be an exponent on that 36, and that 2 is going to be an exponent on that 2. So when I condense it, I get log base 2 of 36 to the 1/2 minus log base 2 of 2 squared. Well, I can work out 36 to the 1/2 because I remember it's power over root, so it's really the square root of 36. Well, that gives me 6. So I'm going to say that the right side is going to change into the log base 2 of 6 minus log base 2 of 2 squared gives me 4. And I still have the log base 2 of 2x minus 1 over x plus 5. I still have it on the left side. So now I'm still not done condensing on the right side. I need to condense log base 2 of 6 minus log base 2 of 4. I see there's a subtraction sign, so I know I'm going to use division. I end up with log base 2 of 2x minus 1 over x plus 5 is equal to log base 2 of, I put my fraction bar. The 6 had a positive log in front of it, so the 6 goes to my numerator. The 4 has a negative log base 2 in front of it, so it goes to my denominator. Now that I have a log equal to a log, they have the same exact bases, I can ignore the logs and their bases and set the arguments equal to each other. So I have 2x minus 1 over x plus 5 is equal to 6 divided by 4. And now I can go ahead and cross multiply. So I'm going to get 4 times 2x minus 1 is equal to 6 times x plus 5. Well, if I wanted to solve this, I would go ahead and use the distributive property. I'm going to distribute my 4. I get 8x. 4 times negative 1 gives me a negative 4 equals 6 times x gives me a positive 6x. 6 times a positive 5 gives me a positive 30. I'm going to go ahead and solve for x. So I'm going to subtract 6x from both sides. 8x minus 6x gives me 2x. My negative 4 drops down is equal to 30. I'm going to rewrite that. So I have 2x minus 4 is equal to 30. Whenever I solve for x, I'm going to add 4 to both sides. I end up with 2x is equal to 34. I'm going to divide by 2, divide by 2. Those go away. I get x is equal to 17. So 17 is my answer. Now, if you check your 17, whenever you plug it in for that 2x minus 1, 2 times 17 gives you 34, minus 1 gives you 33. So that is a positive log. That's okay. And if you were to plug in your 17 for this x plus 5, your 17 plus 5 gives you a positive 22. You can take the log of that, so that's still okay. The only time you can't do it is if when you plug it in to the argument of a logarithm, if it gives you a negative argument, it's impossible because we cannot take the log of a negative number. Thanks for watching as we use the laws of logs to solve our equation.